And let's take a look at counting techniques. Our first rule is the multiplication rule of counting. It says if a task consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second, R selections for the third, and so on, the number of possibilities is P times Q times R, and then it goes on forever, for however many you have. Let's take a look at a problem to understand what this is referring to. It says if a man has 2 pairs of pants and 6 shirts, how many different combinations does he have? Well, here's pants. And here's the shirts. Now there's 2 pairs of pants, so I'll put 2 here. And 6 shirts, so I'll put 6 here. And 2 times 6 would give us 12. So that's how many different combinations he has. This is probably most important for people going into business, so they can plan accordingly. The biggest, was a programming issue, but mainly affected businesses, is Y2K. That's where we were storing off 2-digit years. So like 1989, we were storing off 89. In 95, we were storing off 95, and so forth. And then in our computer programming, we'd check dates. We'd check if this date was less than this date. Well, 89 is less than 95. So then that would be true. But when it came to year 2000, if we stored off the last 2 digits of the year, we'd have 00. Then it was checking if year 2000 was less than 1995. And looking at the last 2 digits, it looks like it is. But it really isn't. 2000 is greater than 1995. Big screw up. Well, the reason we did that is to save space. But we didn't anticipate that the number of possibilities here wasn't enough. We actually needed to store off 4 digits, so it would be enough. Cost huge amounts of money. You can probably Google it and find out what the estimate is. But just unreal how much code had to be written, how much money was spent because of poor planning. And I was a computer programmer for 13 years, so even as late as like 1997, 1998, we were still putting 2-digit years in. So programmers don't tend to plan ahead. I don't know if they anticipate they're going to die next week or what it is exactly, but they don't plan ahead. So if you're going into business and you're working with a computer programmer designing a computer system, you need to do the one planning ahead, because they're not going to plan ahead. They won't think very far. If you here at Cali, we have 6-digit numbers, so an ID number, and then this can be 0 to 9. So, which means we have 10 to the 6 possibilities. Which is a total of 1 million. And that seems like that'd be plenty. But again, you're sitting there trying to plan for the future. Is that really enough? And plus, this is a system we bought from somebody else. So, they're dealing with colleges much larger than Cali. What is at the beginning here is some digits we don't use. I don't remember if it's 3 or 4, but they're 9s. They're always 9s. We don't use them for anything else, but this gives us an additional 3 zeros on there, which then takes us to 1 billion, which would definitely be enough. And if I had 4, then again it adds 4 zeros on here. It takes us to 10 billion. Planning. Even though you're not going to do anything with these digits, they're always 9s. And these can be 0 through 9. That still allows growth in the future. And that's why this section is so important for people going into business. Let's look at this one. says a red and blue electronics device supposed to have 8 on and off switches. How many different combinations can be set? Well, this each one of these is one possibility. It's either on or off, so you can set these however you want. It could be on, off, on, so forth. Well, let's first just look at our blue, and then it'll help us see what the possibilities are. We got 8 switches. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this one has 2 possibilities. Can be on or off. This one has 2. Can be on or off. And actually, all of them have 2. There's 8 of them, so that would be 2 to the 8th. Now, that's just for the blue. But we got blue and red. So our different possibilities, how many different combinations can be set? We can have 2 to the 16th power. That's how many different possibilities there are. I'm not going to actually write that down, whatever it is, but that would give us a number of possibilities. This is used a lot in computers. Blow this up so you can see it a little bit better. This talks about how long it takes to crack a password, and you can see here if we got the length of 2, tells you how many combinations, and it's instantaneous. So if I set a program trying to crack your password, I can get it immediately. 3 would be less than 2 seconds. Some of them down here, like 6 for length, would be 8.5 hours. And if you go out far enough, 15 in length, you see it take them 53 trillion years to break it. Well, where this is, people are always trying to hack in, trying to break in, and so forth. You password protect an Excel spreadsheet, for example, and you forget your password. Well, IT will sit there and they'll try to figure out your password, try to break into it for you, so you don't lose all your data. Well, if you set a 115 in length, 53 trillion years is a long time to wait, so you're never going to break it. But if you set one reasonable, even if it's 7 in length, then they can break it maybe in 9 days maximum. Might be less than that. Okay, so if you've got Social Security numbers and a bunch of retiree information, and you password protect it, and you lose your laptop, for example. Well, that actually happened at Boeing. When my mother worked there, somebody took some work home on her laptop, and it was in Excel, and they'd password protected it, and they lost her laptop, or had it stolen. And they signed up all the retirees, because it had all the retiree information in, whatever you might imagine, addresses, Social Security numbers, so forth. Boeing paid for some kind of credit check program for all the retirees. I can't remember what it was now. My mother didn't have a computer, but I signed myself up with my email address so I could monitor her credit. Big screw up. And of course, the person, I'm sure, was fired. You don't do things like that. But the big concern was nothing ever happened. I mean, there was never any blip on my mother's credit saying somebody had tried to steal her identity. But big worry is, could they break into the spreadsheet? Definitely, if you got something like that, you want something maybe out here 10 in length. So it takes 447 years to crack into it. Definitely don't want one of these lower ones. Well, in terms of network logons, usually they time out, or not time out, but error out. When you enter your password wrong like 3 or 4 times, it locks your account for an hour, or maybe 2 hours. Maybe you have to actually call to get it cleared. So that's kind of gets around this problem, this issue here. But still, password security is very important. In a business sense, you're having to sit there and try to decide what should the password be. What kind of stipulations we want to put on our employees. Obviously, if you set good passwords, you're going to have less people hacking and so forth, unless they actually just give the password away. Let's look at the next one here. Okay. says, given a password that consists of the alphabet A through Z, in case doesn't matter. A, how many passwords possible given the password is 5 letters, repetition allowed? So we have 5 letters. A through Z. So that means we have 26 possibilities for our first letter. Now it says repetitions allowed, which means if I use A here, I can use A here. Which means this will be 26 possibilities, this will be 26, this will be 26, this will be 26, and so we have 26 to the 5th power possibilities. Now B, how many passwords possible? Given the password is 4 letters, repetition not allowed. For example, if I use the letter A, I can't use it again. Got 4 letters. First one is 26 possibilities. Imagine I use A. Well, now there's only 25 letters left. Let's say I use M. Now there's 24 and then 23. And I won't actually multiply those out, but well, actually maybe I will, just to show it. Because if you had never put in an exponent in your calculator, you probably need to see it. 26 to the 5th. Well, if I do 26 carat is how we do a power in a calculator, and then 5th. And 8, 1, 3, 7, 6. So 11,881,376. And here we got 26 times 25 times 24 times 23. And we've got 358,800 possibilities. You can see just by adding another letter here, even though we didn't allow repetition here, take a look at some of the differences in numbers. 358,000 versus like about 12 million. You know, wow, just from one extra letter. I know not everybody agrees with me on computer security in this regard, but personally, I think people should write their passwords down on a piece of paper and keep it in a wallet or their purse. And then if they lose a wallet or purse, then you just reset your password. It's not a huge deal. That's much more secure. Do it that way and have a good password. I mean a good one with numbers and weird stuff in it and so forth. Then to choose a password is just easy because you can't remember a real long one. And not write it down. You know, if your password's happy, you know, well, that's no good. People can hack in and so forth. They were talking on the radio, the most common PIN number. And you might guess what it is. It's 1234. And a good percentage of people leave their PIN numbers as 1234 because they can't remember. Well, wouldn't it be much more secure to actually be able to write down something on a piece of paper and put it in your wallet? Because you know your wallet's disappeared. Probably nobody's going to pick your pocket, steal your wallet in order to get your computer password. They're going to try to hack in. So, yeah, I don't necessarily agree with everybody in IT in that regard, though. They say you should never write it down. Okay, number 4. Social Security numbers of the form, 3 digits, 2 digits, and then 4 digits, where each one is 0 to 9, in theory. Assuming all possibilities allowed, how many Social Security numbers are possible? Okay, so we got this. And each one is 0 to 9. So 1 through 9 is 9 possibilities. And you throw 0 in there, and it goes to 10. So each one of these is 10 possibilities. Now, I know you can't have a Social Security number of all zeros, but in theory. So what was that? 5, 10 to the 9th power, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 billion. And which isn't nearly enough. They didn't plan out far enough for this. They probably should have added another 4 digits to encompass all the different possibilities. And it could be that they figured people wouldn't be able to remember that many digits, which is why they didn't go that way. It's hard to say. But everybody uses the Social Security number system. Students coming into the country, if they partake of financial aid, get any kind of government benefits or even just be tracked in the system. Well, they're given a temporary Social Security number. It doesn't make them a citizen, just gives them some kind of number. Anybody that has to, again, even if they're not a citizen, has to go through some kind of government system, then is given a number. They actually will reuse Social Security numbers after a period of time. I don't know what that period of time is. But again, to rewrite every program across the entire United States with Social Security numbers would be a huge undertaking. So businesses got to plan ahead. They got to think of these things instead of spending $20 billion rewriting this computer system later on. Now, factorial rule. This is a collection of indifferent items can be arranged in order in factorial different ways. And this n exclamation here means 1 times 2 times 3 all the way up to n. I had took a programming class at Wichita State, and the professor was from India, and it wasn't very nice. But me laughing at what happened, but there was a guy in there. He's kind of a smart guy, smart aleck type guy, I should say. And we were to program this into the computer. Not a hard computer program. And the professor was going over that, and the guy said, "I'm not understanding what you're wanting. Now, what do you want us to do with this in?" And the guy went on to explain it, and he said, "Now you don't understand me. What are we supposed to do with this in?" He wasn't realizing that in English this is an exclamation. You say it with more force. I saw the humor in it. It's pretty funny, but not very nice. Well, let's take a look at what in the world does that mean. 5 factorial, for example. We've seen it with the formula there, but 5 factorial means you're going to multiply 1 times 2 times 3 times 4 times 5. So from 1 up to whatever number. Well, that's 120. And put that in. Now you can actually do that on your calculator. If I come over here and I put my 5 in, press my math, and left arrow over to PRB and down arrow to the fourth one, that's our factorial symbol. Press enter on it, and then press enter again, and we'll get our 120. Let's take a look at this problem. It says, how many ways can 6 students be lined up? Well, how many ways can 6 students be lined up? Okay, I got 6 students. And for my first chair, for example, or first lineup position, I'll say chair, just so they're all sitting down. Okay. I got 6 students to pick from. Okay, now let's say Sally goes and sits in a chair. For my next chair, I have only 5 students left because Sally's already sitting in the first one. So 5, and then 4, and then 3, and then 2, and then 1. So it goes down. And this is actually 1 times 2 times 3 all the way up to 6. So this is the same as 6 factorial, which would give us 720. Again, I could put that in my calculator. 6, math, PRB, and then the fourth one, enter, 720. So that's our number of possibilities. Let me save this. I'll start a new page. Page 01. Now, next thing we're going to talk about is permutations and combinations. And these all kind of fit the same form. They're out of this many, whatever that number is, pick this many. So out of n, pick r. So out of 20 students, pick 3. Out of 10 books, pick 5. So forth. Now, first one here, permutations. Here, order matters. And you might think, well, what does order matter mean? Well, if I'm picking 3 people to be president, vice president, and treasurer of the statistics lovers group. And I got this example down below. Then order of matter, because whether you pick first, second, or third, you're either president or vice president, or so titles matter. If you just pick to be members of a committee, well, it doesn't matter if you pick first or third, you're still just a member of the committee. So we'll come back to this formula. Let's take a look at number 7. So out of 10, we're going to pick 2, and that's permutations there. Let's do this on our calculator here, or by hand first. Sorry. Okay, so of this form, the larger number is our n. So this is n, and our smaller numbers are r. So from our formula, we got n factorial over n minus r factorial. Okay, so we said n was 10, so we got 10 factorial over 10 minus 2 factorial. Now that gives us 10 factorial over 8 factorial. Well, 10 factorial, that's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. And 8 factorial, that's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Now after I write these out, you notice they have 1s in common, 2s in common, 3s in common, all the way up through 8 factorial. So up on top we're left with 9 times 10, which gives us 90. Now, of course, if this was 100 factorial and this was 80 factorial down here or something like that, you wouldn't want to write out 1 times itself up to 100. But I just wanted to show this to show the pattern. Well, let's show how to do this on the calculator. To do a permutation, I'm going to put my number in first. I put 10 in. I go to Math, left arrow over to PRB menu, and I want to choose NPR, the second one. And do Enter. And we're picking, how many are we picking? 2. Enter. And that gives us our 90 there. So that's how you do it on the calculator. Now, you might be saying, well, why just let the calculator do it? Sometimes, when you put a factorial in your calculator, it becomes too big. Like if I put in 98 factorial, if I do 98 Math, left arrow over to PRB and 4, and Enter, you get overflow. So sometimes your numbers are such that you have to do it by hand. So that's why I always just show it just in case. I doubt if you run across a problem ever that big, but you never know. Now remember, permutation is order matters. So let's look at this. Now I'll do these on a calculator now that I showed you one by hand. But this says out of a class of 15 students, 3 students are to be picked for president, vice president, treasurer. So out of 15, we're going to pick 3. And order matters, because if you pick to be president, vice president, treasurer, then definitely matters. That says how many possibilities there are. So we got 15, NPR 3, permutation. So let's go put this in our calculator. So 15, Math, left arrow to PRB, NPR. 15, pick 3. And Enter. And we get 2730. So that's how many possibilities there are. Let's look at number 9. It says out of 30 songs, 4 to be picked. So out of 30, pick 4. Or to be picked for the start of a dance. Songs are not to be repeated. How many possibilities are there? A lot of people get this one wrong, because when you start thinking about order, does order matter? And people say, well, no, order doesn't matter. But when you think about it, they start off with this dance with a certain song. I don't know if it's upbeat or slow. I think upbeat to get everybody kind of going. At the end of the evening, I think they usually end with like a slow song, maybe. So they plan the songs, what order they're going to be in. Sometimes that's so important for radio stations, they'll send that planning off to another state, another city, to plan what order should the songs be played in. What's the optimal order that would get the greatest customer satisfaction? So people keep listening to your radio station. So order matters. So we're going to use NPR, our permutation. So let's go put that in. So we got 30, and then math. Left arrow over to PRB, NPR. 30, pick 4 was it? Yeah. And then enter. And we got 657,720 possibilities. Definitely not going to sit down and write out all the possibilities. Okay, let's look at this one. Director wants to pick a play for the fall and spring at the college. She has 12 to pick from. How many possibilities are there? So out of 12, pick 2. Well, why I say 2 is because I pick a play for the fall and spring. So they're going to be different plays. Now, definitely there's probably ones that better go with fall than ones that would go with spring. So the director, when they look at this, order definitely matters. So order matters. So we're going to use NPR, permutations. So 12, pick 2. So we got 12, math, left arrow to PRB, NPR, and 2. And we get 132 possibilities. Number 11. This gets into our next one, the combinations. Now this is still out of N, pick R, but here order doesn't matter. So it doesn't matter what order we pick them in. And we've already alluded to that. We'll come back to that formula. Let's go down to our 11th one here. Out of 8, pick 3. And it's combination. Well, larger number is always going to be our N. So this is N, and this is R. So if I come up here, it says that we want to plug that into N factorial over N minus R factorial times R factorial. Okay, so we got 8 factorial over 8 minus 3 factorial times R factorial, which is 3 factorial. Well, 8 factorial, that's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. Now 8 minus 3 is 5, so that's 5 factorial, which is 1 times 2 times 3 times 4 times 5. And then 3 factorial is 1 times 2 times 3. Well, again, notice the 1's are the same, 2's the same, 3's the same, 4's the same, 5's the same. So that gives us 6 times 7 times 8 over 1 times 2 times 3. And we could simplify this a little bit more. Here we got 3 and 6, they're both divided by 3. 3 divided by 3 is 1, 6 divided by 3 is 2. And we've got 2 times 7 times 8 over 1 times 2. The 2's cancel. There we go. 2's cancel. And that 1 is trivial on the bottom, so I can drop that. So we're left 7 times 8, or 56 possibilities. So that's how you do it by hand. And again, there may be times where the numbers you'd enter would overload your calculator. So you have to do it this way. Let's show how to do it on the calculator. First thing I'll do is we're doing 8, pick 3. So I'm going to do 8, go to Math, left arrow to PRB, and we'll choose NCR, third one. And we're picking, what did I say, 3? Yeah. So then I do Enter, and that gives us our 56. So pretty straightforward on the calculator. Let me save that. And let's look at some more problems. Just did that one. Let's look at this one. Out of a class of 20 students, 4 students would be picked for a representative for the Stats Lovers Club. How many possibilities are there? So out of 20, pick 4. And they'll be picked to be representatives, which means order doesn't matter. If you pick first or fourth, you still just have representative. So it's going to be a combination. So we do 20 NCR 4. And let's see what we get. 20 Math, left arrow to PRB, NCR 4. And we get 48, 45. That's how many possibilities there are. Now this one might be kind of debatable whether order matters or not, but it says if a child can open 3 out of their 10 presents early on Christmas Eve, how many possibilities are there? And let's pretend all the presents are the same size and so forth, so that there isn't any kind of influence there. So order doesn't matter. Pick first or third. It's still just same present. So out of 3 of the 10. So out of 10, pick 3. So we got 10 NCR 3, and let's see what we get. 10 Math, left arrow over to PRB, NCR, and 3. It's 120 different possibilities. Let's take a look at this one. It says if a class has 10 women and 12 men, a committee of 4 women and 3 men are to be chose, how many different possibilities are there? Well, the first one, out of 10 women, we're picking 4. So we're going to have 10 NCR 4. That's for the women. And then for the 12 men, we're picking 3. So out of 12 NCR, we're picking 3. Now this is the different combinations of women, this is different combinations of men, so we're going to multiply those together. So let's see what that gives us. Oops, didn't mean to click that one. Yeah. Okay, good. Got that to go away. So 10, and then Math, and then PRB, NCR. And 10 pick 4 times 12, and then Math, and then left arrow to PRB and NCR. 12 pick 3. So that gives us 46,200 possibilities. I don't know if there's any in this particular book that like that, but I ran across that in another book and kind of liked it, so. Okay. Now let's say we're using the permutations rule. Order matters here, and some items are alike. Well, what I'm talking about here is, for example, look at my name, David. Obviously, order matters, right? David is a lot different than Avid. And some items are alike. See how there's two D's here? That's what we're referring to. How many possibilities are there? Well, let's look at this example. It says, how many ways can Mississippi be arranged? This formula, go back to it. We got n factorial up on top. Now, n refers to how many letters you have total. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we'd have 11 factorial up on top. Now, this first one here is the number of m's. We just have one m, so this would be 1 factorial. This next one is the number of i's. 1, 2, 3, 4. So this would be 4 factorial. This next one is the number of s's. 1, 2, 3, 4. So we got 4 factorial. And then this next one is the number of p's. 2. So 2 factorial. Okay. That should account for everything. This you can't do in your calculator. You have to do by hand. So, well, some of it I could do on the calculator. 11 factorial I could do on the calculator. But, let's see. 1 times 2 times 3 times 4 times 5 times 6 all the way up to 11. 1 factorial is just 1, so that drops away. 4 factorial, that's 1 times 2 times 3 times 4. And 4 factorial here is 1 times 2 times 3 times 4. And 2 factorial is 1 times 2. Well, 1's cancel, 2's cancel, 3's cancel, 4's cancel. So up on top we're left with 5 times 6 times 7 times 8 times 9 times 10 times 11. Down below the 1's are trivial, those are to drop away. And we got 2 times 3 times 4 times 2. Again, I got rid of the 1's. And here's 3 and 6, both divisible by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. Here's 4 and 8. They're both divisible by 4. 4 divided by 4 is 1. 8 divided by 4 is 2. And here I got 10, and here I got 2. They're both divisible by 2. 2 divided by 2 is 1. 10 divided by 2 is 5. Let me write down what I have left. I got 5 times 2 times 7 times 2 times 9 times 5 times 11. And on the bottom I've got just 2. Let me double check that. 5, 2, 7, 2, 9, 5, 11. And I notice that the 2's will cancel here. So we're left with this. 5 times 7 times 2 times 9 times 5 times 11. I'd like to show you my great skills in multiplication, but I don't think I will today. So let me come over to the calculator. 5 times 7 times 2 times 9 times 5 times 11. 5, 7, 2, 9, 5, 11. 34,650 possibilities. And again, you know, right up here, you could have plugged this part in into your calculator. The key is, if you got more than a single number on the top or the bottom, and this 11 factorial will be considered a single number, you have to put parentheses around it. So when you plug it in your calculator, you have to put parentheses around your bottom part like that. A note, in finding probabilities, the denominator consists of using either permutations or combinations to find the total possibilities. Earlier we talked about the number of Social Security. We said it was 10 to the ninth as the number of possibilities. If we were to ask what is the probability somebody will guess your Social Security number, well, there's this many possibilities, and yours is unique at any given time, so it would be 1 over that for your probability. So that's what they're referring to with probabilities. And here's just a recap of where those are located at. NPR, NCR, and our factorial symbol is under the math and then PRB. One last thing. This is actually trying to find different combinations, shortest path, so forth, is used in networking, specifically the internet. If I'm sitting here over in Arc City, one of the hubs of the world, and I want to go surfing the internet to a site over in New York. Well, it may go from Arc City to Kansas City. So it may go like that. And then from Kansas City, it may go over to Chicago. And then go to New York. Well, that's one particular path. Next time I go to that same site, it may go from, instead of going through Kansas City, maybe it goes through Dallas. I don't know. And then it goes to Miami. Miami, Florida. And then goes through New York. So it uses a different path. It doesn't always use the same path. The idea on it is that it's not hardwired in, and not everybody then is flooding this one path out to any sites in New York. So it's distributed. If for some reason Kansas City's having internet issues right here, well, if you relied on one path, then that would clog the internet. Nobody could go to any place in New York. By having this set up such that it takes different paths, then it can it's never down. So if this is down, no problem. It goes this route. Goes another route. Now it's not necessarily the shortest path, but it's not the longest path either. You're not going to bounce from Arc City over to Italy to Australia and then to China before you get to New York, and have 10 minutes before your website comes up. But this, again, this is used. And, of course, the military used it as if a nuclear bomb wiped out Kansas City, then Arc City could still communicate with New York. So that's the way the whole design was set up. Now, when I'm surfing the internet, people watch me. It looks like I'm very impatient. If a site's not coming back fast, I'll sit there and refresh over and over, because I know it's using different paths. And you may run across that yourself sometimes, where it just seems like it's slow, it's not coming back, and you hit refresh, it comes back immediately, and you think, well, that's weird. Well, this is the reason why. Let me save that. In case you're wondering, there is a certain path that definitely takes in part of that, but not always consistent. Let me stop my recorders. And stop my other recorder.